Record. Welcome back. Got some physics and music online cruising on. Let's pick up where we left off. Not really where we left off, but keep on proceeding from where we stopped. So you've taken a midterm at this point, and that is good news. Got that done. We've got a few more weeks of experiments, and then it's basically final project done. So we're going to go over some of the guidelines regarding the final project today. That'll be something that's on our plate, but we're also going to introduce some new material over the next couple weeks and get some, I don't want to say finality in our ability to analyze sounds, but get some more information in terms of how we can look more in depth at sounds and look at sounds that have more depth to them than themselves. So let's just go ahead and we'll jump on over to presentation. Boom, do that. Open this. There we go. All right. So at this point, yeah, we're through section 7. Section 8 was really the midterm. So if we jump on over to our Canvas page, we can see where we are, what's going on. Zip. If it loads up, there it is. Section 7, section 8. Hey, we're down here in section 9. Uh-oh, I better actually publish that. That would be nice. And my apologies, I meant to have that published. But yeah, we're on section number 9, which, as you saw there briefly, has to do with standing waves. So we're going to look at some aspects of standing waves, see how they are correlated directly with harmonics, and expand from there. So we definitely got another experiment to work through this week. Obviously, we've got ourselves the outline and the quiz. Actually, just an outline, no quiz this week, but there is the experiment that has both the results upload and the experiment test. So again, no quiz this week, just the outline and then the experiment. So before we get started here, I think it would be good just to look over the final project guidelines since it's already here so that we can be on the same page with everything. So the final project itself is something that is due by the end of finals. I think it's the Thursday of finals, which would be December 14th is what I have it as. I have to go back and verify that, but it is due during finals week. You'll have enough information to get it done well before finals as well. So that's kind of up to you. You put things off, or if you just get things done. I generally work on deadlines myself where, hey, I got to do this now, so I better do it. But people work different ways, and that's great. So in terms of the final project, each student responsible for submitting an original final project by the due date. At the end of the course, we have the project will be an analysis of a sound or sounds, excuse me, using what we've learned in this course. It definitely requires the use of Raven, and you must include screenshots of the program use that is explaining the analysis that you're ultimately doing. The choice of the project is largely up to you. Some limitations, but in general, it's mainly up to you, though there are some things that I will definitely suggest. Music majors, if you're a music major, it should just fall right into your lap that, hey, you do something with music. If you're a singer, you use your voice. If you play an instrument, use an instrument. I'd say the one thing that maybe wouldn't correlate well with that is that if you're a drummer, drums are a little bit difficult to analyze because they're not composed of harmonics. They have just overtones generally, depending on what type of drum it is. But usually you're a music major, that would kind of be a go-to. I'm not going to really keep track, to be honest, of whether you're a music major or not. So everything is really up to you. But yeah, if you're a music major, I think it just makes it easy. Other majors, do a topic of your choosing, musical in nature or not. I know that the vast majority of people in this course are communicative disorder majors, which I would suggest doing something that's applying all of this to your field of study, but that doesn't necessarily have to be the case. But I do find a lot of times that communicative disorder majors will start doing things with speech sounds, looking at diphthongs, monophthongs, accents, speech impediments, and things of that nature, where you're looking at actual formation of the sounds with the vocal folds and the resonance cavity of your head and tongue articulations and stuff like that. But again, it's up to you. General guidelines are this: it should not just be about pitch and the fundamental frequency. That was stuff that we've done early on. Yeah, finding the fundamental frequency and determining the pitch of the sound, closest musical note. While that could be definitely a part of the experiment or part of the discussion, part of the report, it shouldn't be the focus by any means. So what you want to be able to use is the stuff that we've learned throughout the course. Yeah, we've learned about fundamental frequencies, but we've got all this other stuff. We've learned about the other harmonics. We're learning about timbre, distribution of the intensity levels of the harmonics, power ratios or intensity ratios. There's all sorts of things that we've looked at up till this point that would be things that I would expect to find to some degree within a report at the end of the semester. There's some more stuff that we're going to do that'll give you some more ideas, but ultimately that's it. You should be, in a sense, producing results for your own experiment in a way. Like you're coming up with what you're going to focus on, what you're going to analyze, and then you do some thorough analysis of it. Write up screenshots, explanations, tables, and that's it. So I will say that there is a word count that must be taken into account. 1,000 words for the report, 1,000 words or more is what it is. More is not necessarily better, but generally looking for something that's substantial in its information, and thus likely you'll end up with more than 1,000 words, but at least 1,000 is mandatory. Otherwise, there starts to be deductions for percentages beyond or under 1,000 words. Yeah, topical outline. So this is sort of an outline to guide you in the composition of the report itself. This isn't to put in your report these words here to copy and paste into your report and then answer these questions. These are here to guide you to answer your own questions in your words and put in results and stuff. So first off, you should have a title for it. That's kind of up to you. What are you looking at? That's always a nice title. An introduction to what you're actually analyzing. Is it a comparative analysis where you're looking at, hey, my mom says this word, my sister says this word, their voices sound the same. Let's pick out a little part of those two voices or those two words that they say and compare them and see if they do have the same pitch, see if they do have the same timbre for that little portion. But that would be where you explain, introduce just what you're doing. You got the setup and parameters. What are you using? What sort of equipment? Obviously, Raven, some sort of a recording device if you're recording the sound yourself, and any special configuration that you're utilizing to get your data. Then number 4 is where it's really the bulk of the actual report itself, is where you discuss, hey, what did you measure? What did you observe? You present your data, provide tables, provide screenshots, explanations of the screenshots, show what the results are, and discuss said results. Like, hey, this is what these results are showing us. This is the information I've extracted from looking at what Raven shows me regarding the sound at this particular point in time, focusing on this particular aspect of a sound. From there, a little discussion, conclusion. What can you conclude? What did you learn? What did you discover? Evaluate the outcome ultimately in some objective way. And that's it. Make factual statements and go from there. In terms of the appendices, I'm not really a stickler on that. This isn't an English class per se, but physics class. It's generally a good practice to cite anywhere else that you've gotten information from or that you've utilized in your report itself. So I would recommend, citing information that you've received from other sources. But in terms of doing footnotes and stuff like that, don't even worry about anything like that. Format wise, I'm not really particular about either, as long as it's following this general outline type. should be good. Definitely, once again, screenshots, explanations of the screenshots. That's where a lot of the data is itself, in the screenshots and in the explanation, as well as tables. In terms of picking something, again, it's largely up to you, but I'll give you some advice on what not to pick. Don't pick a band playing a song. There's too much going on. If you have multiple instruments playing simultaneously, drums, guitar, bass, and someone singing, maybe some other background sorts of computerized sounds, it's just too much to weed through. I would generally say keep the sounds that you're looking at singular source sounds, one source of the sound at a time. Unless you're looking at something specific like a guitar chord or a musical chord on some musical instrument like a piano, where you can look at how the individual frequencies sort of bind together at certain frequencies and produce a pleasing response, a nice harmonic chord in a sense. Otherwise, it gets to be where you can't really discern what's what, with a sound file with multiple sources of sound. So I would suggest keeping things singular. And also, there are some things that just make the analysis easier, like doing something that's comparative. Comparing two sounds to one another gives you things right off the bat to talk about because you're comparing them. Hey, what's in this sound versus what's in this sound? Comparing two people's voices or a vowel sound of two different people's voices. Comparing a particular speech sound that two different people make, or comparing two different speech sounds. It gives you stuff just naturally to talk about, naturally to look at, because again, it's just comparative. If you're doing something that's just one singular sound, that's fine too. You've got stuff that you can talk about. You can still look at intensity level distributions. You can still look at all sorts of things pertaining to it in terms of what you hear versus what you see in an analysis. So I don't want to dissuade anybody from doing that, but just plain and simple, if you are struggling to come up with something, look for something comparative. A piano note versus a guitar note that's the same exact note. Why do they sound different? You start looking at the distributions of the intensity levels of the harmonics. There's all sorts of stuff in there. But that's ultimately what you want to start thinking about. It's not due for another month and a half, just about, but comes up quick with Thanksgiving, and November is always just a really quick month in general. And then December comes, there's finals, all this other stuff. So just start milling it over in your head. And yeah, that's pretty much what we've got going on. Questions with that? It's kind of a lot of information right there, but and we'll discuss it some more next week and the week after. But just to kind of put it out there right now. All right, so let's get to today's material then, shall we? Sure. Well, topics for today, we want to look at resonance and standing waves, and then the section 9 experiment. We already did the final project part, so we'll just get right into some standing waves. What is a standing wave? Well, a standing wave is a wave that looks like it just stands still in one place, that it doesn't move side to side, that it just oscillates up and down. So we've actually looked at some standing waves before. Let's go ahead and open up this little simulation here where we're looking at frequencies of harmonics. This is a standing wave. It doesn't look like it's moving side to side, but it's actually composed of a wave moving to the right and a wave moving to the left, simultaneously overlapping in phase with one another, such that it just looks like it moves up and down. Standing waves on strings and standing waves in air columns are directly correlated with harmonics. Because standing waves in strings and standing waves in, I should say, cylindrical air columns or musical air columns, I want to be a little careful with that, produce harmonic tones. So this would be what we could call the n=1 standing wave, or the first harmonic, or the first order standing wave. but the n there is the harmonic number. And it just gives us, again, the correlation of what particular pattern we're looking at. This would be a string that's fixed at both ends. I could clear this off and then say, hey, let's look at the n equals 2 standing wave. N equals 2 standing wave, second harmonic, looks like this. If it's a string that's fixed at both ends, there it is. Individually, we could look at the n equals 3 standing wave, so on and so on. We'll just pop up, there's n equals 5 standing wave. N equals 5 standing wave, fifth harmonic has 5 times the frequency of the first harmonic. That's what we know about harmonics. So what we want to be able to get out of this is not just the harmonic number, but also an understanding that the standing wave pattern itself is discretely connected with a harmonic. That's what harmonics are built of, standing waves. Of course, when we put multiple standing waves together, there I just put the fourth harmonic together with the fifth harmonic. Now what do you see? Now it looks like it's moving to the left and to the right, or to the right and to the left, bouncing back and forth. But because these are harmonics, it still does the same thing over and over, because these are two standing waves that are interrelated with respect to one another. It preserves this cyclic pattern. But individually, it looks like they just both stand still until, again, you start adding them together, and then you get more complex sorts of oscillations that are being produced. Still cyclic or periodic. So that, again, is just going back to standing waves. And ultimately, it's due to an incoming wave and a reflected wave overlapping in space and producing interference that gives us the standing wave pattern. So let me change this to a different simulation here. We'll look at this from the University of Colorado Boulder. They've got some nice simulations just so we can kind of see something regarding wave properties and reflection. And dun, 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 dun. Where is it? There it is. Waves on the stream. Minimize that. So a nice little simulation that just shows how waves behave when they're on a string when we've got a fixed end here. So you can think of this again as the fixed end on a guitar string or fixed end on a piano string, violin string, whatever you want, some sort of stringed instrument, and we can produce a little pulse. So I produce this pulse here. The pulse travels and then it undergoes an inversion and it reflects back. Now, right now, there was tension in there which dissipated it, but I'm going to take, excuse me, not tension, there was dampening that dissipated it. The tension I'm just going to leave like this, that controls the wave speed, but we've got this. And what happens is this triangular wave, it's very synthetic, but what happens when it hits these boundaries is that it undergoes an inversion. Inverts, because the boundary itself can't undergo any motion itself, can't undergo any up and down displacement. So that first is this inversion. What happens if we have two of these going simultaneously? Like right when the other one's coming back, I produce another one. See, they start overlapping in space when one's going across the other one. And what happens? It looks like the wave gets kind of weird all of a sudden, but then they both pop back out. So that's called interference. And the interference is just the overlapping of the waves spatially at one instant in time. They just add together to produce some other pattern. So what we want to be able to do is this, not have these little triangular pulses, but have some sort of sustained oscillation that's taking place like this. And right now, what you have is not quite a standing wave because we don't have exactly the right frequency, but you've got this wave that's incoming going to the right and reflects back off of the system and then overlaps with the waves continuously being generated and produces something close to a standing wave. To get this to be an exact standing wave, we'd have to change the frequency to be a specific amount so that we always get that they're overlapping, and then you get something that is just increases the amplitude quite a bit, and that's it. So this looks fairly standing, not completely. There's a little offset still, but it looks like it's just moving up and down, right? So really, if we restarted this and turn this into some slow motion, we could kind of see this incoming wave here strikes, undergoes an inversion. It's going to reflect back, but as it reflects back, it overlaps with what the incoming wave's already doing, and you just get that everything's in sync, or at least in this case, really close to being in sync, where you get this sort of standing wave. Again, it's not perfectly in sync, but hopefully that gives you a picture at least of how these standing waves are produced on strings individually. Now, of course, if you have more than one standing wave being produced that are harmonics with respect to one another, you will have yourself something that is moving back and forth. I can't do that with this program, but we did it with the last one that we looked at. So again, standing waves ultimately due to interference of two waves, an incoming and a reflected wave. And they can happen to waves on strings, and they can actually happen to waves in air columns as well. And that's what we want to start looking at. So let me go back to this. And what we're going to do is not go through all the physics and math that correlates with this, just because it's not, I don't know, the background probably not there. We do just want to be able to extract some information out of this, extract a relation in a sense. So what you start doing with standing waves is you start looking at the smallest amount of a full wavelength that you can fit in the scenario of a fixed string fixed at both ends with a certain length condition. The smallest section of a wave that we can fit in under the restriction that it is bound at both ends would be a half of a wavelength. This right here is a half of a wavelength, and this would just oscillate up and down. So the dashed line here is just saying that sometimes it occupies down here, sometimes it occupies up there. This is like that first harmonic that we're looking at in the very beginning, just like almost like a jump rope, just going up and down, up and down, up and down. Then you could look at the next possible pattern. The next possible pattern would be a full wavelength, because we need it to go back up to where it started and start where it started and have those be the bound ends, which are generally referred to as nodes, locations where there is no displacement. So now we'd have this portion goes up and down, this portion goes up and down. That would be the second harmonic. We'd have that the length of the string is still L, but now we fit a whole wavelength in there. The next one would be 1.5 wavelengths fit, which would correlate with the third harmonic, and then 2 full wavelengths fit, which would correlate with the fourth harmonic, and we could keep on going with this. And what we'd turn out to find if we went through the physics and some math with this is that there are certain frequencies that correlate with these particular standing waves under the restriction of a particular wave speed and a particular length of string. Now the wave speed, that's V right here. How fast the wave itself travels across the string, this V right there. N's just the harmonic number. Is it the first harmonic, the second harmonic, the third harmonic? So F sub n is the frequency of the nth harmonic. It's the first harmonic. This is F sub 1, and we have 1 times V over 2L. L is the length of the string. V is the speed of the wave on the string. When we're talking about waves on strings, the speed of a wave on a string is actually dictated by the tension in the string and the linear mass density of the string. We're not going to worry about that much, but ultimately the tension is how tight the string is, and the linear mass density is a function of what material is the string made of and what's the thickness, the gauge, if you will, of that material. How much mass per unit length is there? But those two things ultimately come together to dictate how fast the wave itself travels on a string. That's controlled by the conditions outside of the frequency. So we set up a particular string, has a certain tension, has a certain length, and right away there are certain frequencies then that correspond to the first harmonic, the second harmonic, the third harmonic, and the fourth harmonic, and so on and so on and so on, given by this expression right here. If we know what harmonic number we're looking at, there's N. If we know the wave speed, that's our V. If we know the length of the string, that's our L. And that's pretty much that. So fundamental frequency, once again, that's the first harmonic, which would be F sub 1. The second harmonic would just be, well, N would be equal to 2 instead of 1. So if we went ahead and looked at all these harmonics that are possible, N is equal to 3, N is equal to 4, N is equal to 5, ultimately we would see that all those higher order frequencies are just the order number or the harmonic number N multiplied by the fundamental frequency. And again, that's stuff that we know. We know that all the higher order harmonics are integer multiples of the fundamental frequency. But here it is sort of spelled out mathematically that higher order frequencies, F sub n, is equal to the n number, the harmonic number that is, multiplied by the fundamental frequency. Pretty cool, right?
I have a question.
Yes.
For the equation on top, so V, when you say wave speed, do you mean like period? Is
No,
it the
wait. So it would be how fast the wave is moving through space itself. So think about like a
Oh,
water wave at the
11,
ocean. Yeah.
so
How fast it's moving
1128.
towards shore.
Okay, got it. So 1128 then basically
That would be for if we're talking about um
in
the
air.
speed of sound in air. Yes. Yes.
Okay.
So for this particular thing, where we look at standing waves on strings, it would be how fast the wave travels across the string. Um, when we look at air columns, which is coming next, then we know that the speed of the wave is the speed of sound.
Hmm.
So if we went back to go back really quick to this, and I want to restart it. I want to do no end and just do.
Also, I have a question. I'm sorry.
That's okay.
Last one. Are we gonna have to know that equation for the quiz or
So there
that?
is no quiz, but you will need to be able to
All right.
utilize it for part of the experiment. Yes.
Okay.
And I will spell it out how you're going to utilize it as well. And it's just a couple times, little baby things, not I shouldn't say baby things, little calculations, but you have to be able to put in your calculator right and stuff like that.
Okay.
So good. I'm glad you asked that question. So the wave speed of this particular wave would be how fast these pulses are moving to the right. So if we said like this was the distance from this beginning dash line to this dash line was like 10 feet, then we'd say, well, how long does it take this one to travel 10 feet? And say it takes 1 second, 2 seconds, 3 seconds, 4 seconds for that pulse to go from here and travel all the way down to here. We'd have ourselves that it travels 10 feet in 4 seconds, which would then be 2.5 feet per second. So that's how we gauge the wave speed of a wave on a string. When we're talking about waves in air, sound waves in air, that's already set. That's 1128 feet per second. Great.
I'm sorry, how did you just calculate that?
I just made something up. I said if we said that the distance from like right here all the way over to this last dash line right here was
Yeah.
10 feet,
Mm-hmm.
counted how long it takes this pulse right now to travel from where it began all the way over to this point right here, and said that that was 4 seconds, for instance, then we'd have that it traveled 10 feet in 4 seconds. 10 divided by 4 is 2.5. So it traveled 2.5 feet per second.
Oh, I see.
So that's just kind of a for instance. Cool. All right. So what we want to do is actually not focus our attention on strings because it sort of is difficult to gauge what the speed of the wave is on a string. When we go over to air columns. Air columns, we know that the speed of the wave within the air column is going to be that of the speed of sound, 1,128 feet per second. So that speed we know then. Great. We can do the same sort of analysis regarding the waves that can fit within an air column, but it turns out for an air column, there's two different types. There's going to be an open air column, where it's basically a hollow tube, open on both ends, so you can see all the way through it. And then there's another air column that we could have standing waves within that's open at one end, but closed at the other. So one end's capped off, the other one is open, so it's more like a I don't want to say like a glass, but something like a cup, but more of a tube in a sense, something that could contain water in a way. So those are the two different types of systems that we could look at, open or open closed. And those two different systems have two different boundary conditions. What happens at the ends? So at an open end, we must have what's known as an antinode. Antinodes are locations where we'll have the maximum displacement of the air molecules. So at the ends, the air molecules here can move back and forth a maximal amount. As we get closer and closer to the center, the air molecules displacements back and forth get smaller and smaller and smaller and smaller until we're right here. At this location right here, that's known as a node. And nodes are locations where the air molecules themselves undergo no displacements at all. They stand still. They're just bound at that one position. And then we go towards the other open end, and the amplitude of the air molecules oscillations gets larger and larger until it's the largest at the very end. So that's just the conditions for open. At open ends, we have to have antinodes. So again, we go in and look at what sort of wave shapes can we fit in here. And it turns out that looking at this is half of a wavelength right here. So we could have one half of a wavelength. This is actually right here a full wavelength. Then we got 1.5 wavelengths, then 2 wavelengths, then 2.5 wavelengths. And it ends up being the same exact correlation that we just had with respect to the standing waves on the strings. So we get the same expression overall, that the frequency of the nth harmonic is the harmonic number n multiplied by the speed of sound in air now, v, divided by 2 times the length. And we still have got a set of harmonics depending on the n number. We've just got that the nth harmonic is n times the fundamental frequency. So that's sort of the picture with this. If we wanted to look at what standing waves look like inside an air column, we can jump on over to Dr. Dan Russell's acoustics page and look at a standing wave in an air column itself. It's kind of lagging up a little bit here, but this would be a standing wave in an air column that's closed at one end and opened at one end. So this open end, you've got the maximum displacement of the air particles. Yeah, that they move in back and forth the biggest or the most that they can. And then you've got these other locations where you have that there is no motion of the air molecules themselves. If you look at this little red dot right there, it doesn't move back and forth. It's at a location known as a node. There's no displacement of that air molecule or any of them that are along that line there. But then there's these other portions where you undergo maximum displacement. They move back and forth by a maximal amount. So that's ultimately what standing waves look like in air columns. You can have an n equals 1 standing wave right here, where you've just got everything moving overall. At the end, you got maximal displacement of the air molecules, and as you go inward, it gets smaller and smaller and smaller until you're at the very end where we've got it that it's capped off, it's closed end. At the closed end, the air molecules can't move back and forth because there's a cap there. There's something restricting them. So we would have to have a node there. So anyways, that's what standing waves in air columns sort of look like. And just wanted to get an idea of what that looks like. And note that, yeah, we've just got different harmonics that can be produced within an air column itself. If we go over to an open closed system, we have something very similar, except we have to have an antinode at the open end and a node at the closed end. That boundary condition gives us different wave shapes or different amounts of full wavelengths that can fit into the tube. So this here, what's shown is actually a quarter of a wave. So we've got the smallest amount of a full wavelength that can fit into an open closed tube is the wavelength divided by 4, a quarter of a full wave. The next one is going to actually be 3 lambda over 4. So we'll have half of a wavelength plus another quarter. So we'll have 3/4 of a full wavelength, then 5 quarters, then 7 quarters, and so on and so on and so on. And what this ends up giving us is that the frequencies of the nth harmonics are given by this NV over 4L now. But there's an extra portion with this. Here, n can only take on odd integer values. There are no even values or even harmonics for an open-closed air column. Open-closed air column will only produce odd harmonics. First harmonic, third harmonic, fifth, seventh, ninth, 11th. There are no even integer multiples of the fundamental frequency for an open-closed air column. And it's just what naturally happens with respect to what's possible in terms of standing waves. So that's just something to take into account. Open closed can only have odd harmonics, where an open can have the full spectrum, even and odd numbered harmonics. What you're going to ultimately do in one of your experiments, or in this experiment, is you're going to listen to some sounds of air columns making little sounds. I mean, I'm going to activate some sound within an air column, and you are going to try to deduce what the length of that air column is. And how are you going to do that? You're taking this expression here, F sub n is equal to NV over 4L, looking at the first harmonic, so F is equal to 1, and then solving this out for L. When you solve this out for L, this is what you get right here. Sorry, I keep clicking off of something. You get this expression. L is equal to 1, that's our n value, first harmonic, 1 times V. V is going to be our 1,128 feet per second, the speed of sound in air. That quantity divided by 4 times the fundamental frequency. So this would be F sub 1 here because we're saying n is equal to 1. So the idea with this is within Raven, you will listen to the sound of resonance in an air column, and then you will measure out what the fundamental frequency is. We know that there's 3 different ways that we could obtain that. I would highly suggest that you use all 3 and make sure that you're getting the right quantity. Look at the period of the wave, extract it from that. Look at the
spectrogram.
Was that
The spectrogram?
Look at the spectrogram slice for the lowest frequency harmonic, and then you can also look at the spacing between adjacent harmonics in the spectrogram slice. I would stay away from using the spectrogram itself for trying to find the fundamental frequency. It's much, much easier to look at the spectrogram slice and the waveform for that matter. But you're going to measure it out. Measure out what the fundamental frequency is. Then you'll go 1,128 feet divided by 4 times the fundamental frequency. This 4 times the fundamental frequency here, if you're putting it all in your calculator at once, you need to put parentheses around that. If you do 1,128 divided by 4 times F without parentheses around the 4 times F, your calculator will take 1,128, divide it by 4, and then it will multiply it by the frequency. That's not what you want it to do. You want it to divide it by both 4 and the fundamental frequency together. So something that you could do is multiply 4 times the fundamental frequency, have that numeric value, and then do 1,128 divided by that numeric value. Yes, Luke.
Could you clarify the two characters in the equation you have highlighted next to the 4 and between the 1 and 1128?
Are you talking about in this portion right there?
No, the previous one you had highlighted. Is that a multiplication, plus sign?
Oh, the asterisk.
That one.
The asterisk
Yeah,
is supposed to be a multiply sign. 1 times 1,128 divided by 4 times, and then it would be 4 times f.
got it. Okay, thank you so much.
Got it. So it's going to ask you to do this for both something that is open closed. This is the expression right here for the length of an open closed tube based upon what the fundamental frequency is. Measure the fundamental frequency, do this, and you get the length. That length will be in some number of feet. That's fine. You'll get some number of feet. For the open system, if we go back here, you're going to have almost the same expression. But if we solve this for L, instead of getting, we need to put it in, keep not doing that. Instead of getting, spread that out. Let's do that for you. So this is our L. L is going to be equal to this right here. It's going to be the speed of sound in air divided by the quantity of 2 times the fundamental frequency. So that would be the length of the tube when you're utilizing the open sound file. So this will again be something that's asked for within the experiment, ask you to quantify what's the length of the tube based upon what you measure the fundamental frequency to be. And again, it'll come out in some number of feet because the velocities in feet per second and the frequencies cycles per second. And that'll all give us feet in the end. All right, so given that, that is pretty much the extent of things. Just some different things to note here between open and open closed systems. Often an open system will be called a half wave tube because the smallest portion of a full wave that can fit in it is a half of a wavelength. And then an open closed system is called sometimes a quarter wave tube because the smallest portion of a full wave that can fit in it is quarter of a wavelength. The difference between the two in terms of the frequencies that they produce is really within the length of the tubes themselves. If you want to produce the note C4, which is about 261.62 hertz, the wavelength of that is going to be 4.3 feet approximately, no matter what. That's the wavelength in air. In order to produce that with a half wave tube, you need a half wave tube that's 2.15 feet long. Whereas if you're going to do it with a quarter wave tube, hey, you only need something that's 1.075 feet, which doesn't seem like that big of a difference, but really the half wave tube is 2 times the length of the quarter wave tube. Once you start getting into really low frequencies, C2 and C1, look at the difference is in what the lengths are. You've got for a quarter wave tube producing the note C1, you need it to be 8.6 feet long. If it's a half wave tube, open, you need it to be 17.2 feet long. And then you go back to, well, where are these cylindrical air columns going to really come into play? And they're right there. They're in pipe organs. Pipe organs aren't used a whole bunch anymore, but they're still around. There's some really big ones. I think there's about 3 or 4 full-size pipe organs that are all half wave tubes, where you have to have these huge pipes in order to be producing these really low frequencies. But most of the pipe organs around are quarter wave tubes. What's the difference in how they sound? The half wave tube pipe organs are more full sounding, more rich, because they have both even and odd integer multiples regarding harmonics. Whereas the quarter wave pipe organs, each note only has odd harmonics in it. So it's not as rich. It's missing harmonics from the spectrum, and the timbre of it just doesn't sound quite the same. But that's pretty much it. They both sound nice though. So with this, we get into resonance. And what is resonance? It's just the tendency of a system to oscillate or vibrate at certain frequencies with large amplitudes. They're basically natural frequencies of the system. The frequencies that things want to vibrate are the resonant frequencies. To resonate is just to produce the sympathetic vibrations, create standing waves at certain frequencies. Resonant pertains to the portion of an instrument or the voice cavity that projects the sound, and then the resonator is the part of the instrument that projects sound into the surrounding space. Resonant, resonator. So I think I just said resonator for resonant. Resonant just pertains to something that can project its sound well. It's resonant. The resonator is the portion that projects the sound. So not going to be tested on that, but again, it all comes down to resonance, being able to sustain and produce substantial amplitude oscillations of standing waves. So what do you need for sound production? Hey, we went this over in the very beginning. You need some source of energy. You need something that produces the vibrations. And then you need something to emit the sound itself. What's vibrating? Well, if it's just a string that's vibrating, you think about maybe trying to play a guitar that's an electric guitar that's not plugged in. I pluck a string of an electric guitar that's not plugged in. It's a very weak sound. It's not really loud. I can hear it, but if I take an acoustic guitar and pluck the string, it's naturally a lot louder. And the question is, well, why would the acoustic guitar be louder than the electric guitar that's not plugged in? And it comes down to the structure and its ability to resonate, its ability to project the sound outward. The electric guitar that's not plugged in, only the strings really vibrating. Maybe the body of the guitar vibrates a tiny, tiny bit, but it's mostly the string that's coming into contact with the air molecules, making them vibrate as well. And that's it. Whereas the acoustic guitar, you generally have this big pocket of air right below where you're hitting the strings, where the strings are vibrating vigorously, that picks up the vibration and vibrates itself, that air column itself, which also makes the body of the guitar vibrate because it's a hollow body. So you ultimately get a larger amount of vibration so that there's more air that comes into contact with the vibration, thus more air coming into contact with the vibration, more intensity, it's louder. And that's just a kind of what we've got going on with resonance. You got the same thing with like violins. You got these nice little holes in the violins that can capture the vibration, and then you got the whole structure of the violin itself ultimately will vibrate as well. And that overall vibration just comes into contact with a lot more air molecules, makes a lot more air molecules vibrate back and forth at the exact same frequencies that the string is, and projects the sound a lot better than as if you covered those holes up or made a solid bodied violin. So resonant systems, in terms of instruments, we have tuning forks. Hit the tuning fork vibrates. But if you were to touch the tuning fork to, say, a cardboard box or a table, it would appear to be louder because the tuning fork's vibration would be picked up by whatever it's in contact with. And when it's in contact with, it begins to vibrate too, again, activating more air molecules, intensifying the loudness of the sound. Pianos work the same way. Hey, you gotta press a piano key, a hammer comes down and strikes a string inside the piano, and the string vibrates. If it was just the string vibrating, pianos wouldn't be that loud, but pianos are pretty darn loud. You press a string, bam, you hear it. You definitely hear it. Why? Because in pianos, there's this big slab of some kind of stone, generally marble, something really, really solid, that's a soundboard basically that can pick up the vibration of the screen of the string and produce the same vibration itself. And it covers a much, much greater area. So it comes into contact with a whole bunch of air and again projects the vibration. Same with the voice. You've got your diaphragm, you've got airflow that produce the vibration of your vocal folds. And then your head cavity itself is the resonant cavity. It allows the projection of the sound outward. And there you go. If you try to talk with your mouth closed, things get a lot quieter. There's no resonance outward. Or you cover up your mouth, reduce the resonance, reduce the correlation with the projection of the sound. Pitch selection in instruments, some of that depends on what kind of instrument you're talking about. You're talking about some woodwind or some brass instrument, clarinets, trumpets, trombones. It ultimately comes into play with what is the length of the air column itself. Stop selections, where you're putting your fingers, or for the case of like a trombone, how far out you have the armature or how far in. That is dictating what sort of constraint you have on the air column. And well, the constraint on the air column or the length of the air column is dictating what the fundamental frequency is. There you go. That then defines the pitch. For something like a piano or a guitar, violin, etc., it's really a matter of the length of the string. You go to a guitar, you don't put your fingers on any of the strings and you pluck it. It plays one sound based upon the length of the string and the speed of sound across the string, or speed of the wave across the string. But then there's frets on the guitar where you can push down and effectively shorten the length of the string, which then changes the pitch. The shorter the string is, the higher the pitch is. And ultimately you get the same thing with a violin and a piano, but the piano strings are already, for each particular key, the piano string has a particular length and a particular linear mass density for that matter. Then you got structural resonances like bells and xylophones, where it's the structure of the instrument itself that ultimately resonates, that is the resonator. So from here, what we want to do is look at the experiment, talk about it a little bit, and then that'll be that. So there is some reading, air pipes, standing waves in Johnston, 183 through 190, 147 through 151. And this should say experiment, section 9 experiment. I changed how I'm naming things in section 9 experiment guide. So definitely read through experiment 9, section 9 experiment guide, because all the goodies are in there telling you what to do. I'm just going to go over, in a sense, what you're going to be looking at, how you're going to approach it, what to expect, and then we go from there. So there are really four different sounds that you're going to look at in this particular experiment. You're going to look at the sound that an empty bottle makes when it is blown across, ultimately activating some frequencies within it. You're going to look at a quarter wave pipe. You're going to look at a half wave pipe. And then you are also going to look at your own voice, you producing a vowel sound. And that vowel sound that you're going to look at is ah, like you're going to the doctor. Say ah, ah. That's it. So those are the four sounds that we're going to look at. 3 of them are sound files that you're going to get from our Canvas shell. The last one you're going to produce yourself. So I will clue you in on how exactly you're going to do that, but let's just kind of go through this. So first off, there's a bottle. And Dang it. I'm fresh out of bottles. Nothing empty enough to do. Well, perhaps you've done it before or you've seen somebody do it, taking some bottle, it could be an empty water bottle or a Coke bottle or something, and blowing across the top of it or blowing down into it. It has to be just right, but if you can blow into the bottle just right, it'll produce this nice resonance, this nice sort of foghorn sound. Ooh, something like that. That's my impression of a foghorn bottle sound. But what you can do is, if you can try this, what I'd like you to do is do that and blow across the top of it, somewhat down into it, and you can feel the vibration of the bottle itself in your hand. So I would say take yourself a 500 milliliter water bottle that's empty and try to blow across the top of it and see if you can get the resonance to occur. And I'm still looking around for a little bottle. Yes, I do not have one. All right. Anyways, you don't have to record it. It's just something for you to try so you can hear the sound and you can feel the vibration too. It's pretty cool. So that's one thing. There'll be a sound file pre-recorded you're going to look at. And then there's something else you can do. You can take yourself a cardboard or plastic tube, like something empty paper towel roll. Empty paper towel roll, you got a little cylindrical cardboard tube. And what you can do is you can cup your hand and strike the end of it. And you will get this resonance that travels through it. You'll get this little boop, boop, boop. And what that is ultimately a very short-lived standing wave, but a standing wave nonetheless, that gives you sort of an open closed system. If you take your hand and you cup it over and keep your hand on it, it's considered an open closed system. You're activating the air inside it and forcing an open closed system. Or you can take it and tap it on your head or flick it a little bit and you get it to produce an open correlated sound. So those are just some things that you can do around the house. See, I got a big tube right here. So this is an open tube. So I was just kind of hitting on my head there. Doesn't really work that well, striking it. But then I can also go like this, where I can take it and hit this end, then it's open, or if I cut my hand over it, anyways, could keep on playing around with that, but produce a certain sound, depending on whether I have it be an open system or an open closed system. So you can kind of play around with something like that. But what you are going to do is go over to Raven. Oops, that's not Raven. Close that. Eating up lots and lots of things. Don't need my teams. We want Raven. Come on, Raven. There we go. So we'll open up some Raven here. Let me go back over just to our course page. Did I close that? I must have closed that. And just take a quick look at the guide just to see what we're looking at. And then we'll go through what you're going to be doing. Coming on down to section number 9. Section 9, experiment guide right here. Kaboom. And we have it opening. There it is. So there's definitely some text to read over. I'm leaving that to you. That is for you. Then we got an empty bottle. It tells you to go ahead and try to do it, but some people have problems. Some people know how. It's really with an articulation with your lips across the bottle, a certain articulation of your lips across the bottle that needs to take place. But nonetheless, there's a sound file. So what you're going to do is you are going to download and save the bottle resonance sound file from our Canvas page. You're going to open it up in Raven, and you are going to zoom into the sound at this particular time, 0.680 seconds. If you look at a different moment in time, you're going to see something different than you want to be looking at. So make sure that you're right around 0.680 seconds in the sound file. Zoom in so that you can see 3 to 5 complete cycles of the wave, and then get our spectrum slice locator line or time selector line positioned at the 0.680 seconds so that the spectrogram slice shows us specifically what's in the sound at that moment in time. We're going to go focus on the first 2000 hertz frequency wise within the spectrogram slice. So you can just zoom into the first 2000 hertz. And then what you're going to do is highlight one full cycle of the waveform and of the wave in the waveform and place the frequency measuring tool on the first harmonic in the spectrogram slice. And you should ultimately be able to calculate the fundamental frequency from the waveform, from getting the period, and see that it is approximately or within reason the same fundamental frequency that you are denoting in the spectrogram slice. That should definitely be the case, but ultimately, boom, take a nice screenshot, boom, make a screenshot of the bottle, fundamental frequency marked by the frequency measuring bar, and going from there. Show the entire Raven display. You'll be asked for the screenshot. Great. Also, write down the frequencies of the first 4 harmonics as measured from the spectrogram slice, and note that they may not be totally harmonic. This is a water bottle that this was gotten out of. Not a perfect musical instrument, not completely cylindrical. It's going to have some blobby, messy portions of it in the spectrogram slice. Not really nice, sharp harmonics, but you should find that the first 4 frequencies within reason are very close to being integer multiples of the fundamental frequency. They're a little off, but hey, it's not a perfect system. So you're just going to note what they are. Hey, the second harmonic seems to be this frequency, third harmonic seems to be this, fourth harmonic seems to be this. And write those down in the description. Then you're going to download and open the sound open system, going on over to 0.340 seconds. Again, you're going to highlight 3 to 5 full cycles, or zoom into 3 to 5 full cycles. And then zoom into the first 1500 hertz in the spectrogram slice. Adjust your vertical zoom levels, all that stuff, so you got a nice view of the spectrogram slice, and the first 4 harmonics can easily be identified. Going to do the same thing. Ultimately, taking a screenshot, things marked. We've got a full wave cycle highlighted in the waveform. Got the first harmonic marked off in the spectrogram slice, and going through them. Going to do the same thing with the open-close system. However, with the open-close system, you are going to be looking at a different moment in time. Again, pay really close attention to the points in time that you're supposed to zoom in and produce spectrogram slices. And this one, you're going to look over a larger frequency band, first 3000 hertz. And the reason for that is, for the open-close system, one, we're only going to have odd integer multiple harmonics. So there is no second harmonic. There is no fourth harmonic. So it says this. It says, in the spectrogram slice, zoom into the first 3000 hertz and adjust the zoom level so the first 4 harmonics can be easily identified. The first 4 harmonics are not the first harmonic, second harmonic, third harmonic, and fourth harmonic. This is an open-close system. You're going to go through and you're going to see, hey, there's the first harmonic. The next one is not the second, it's the third harmonic.
Okay. And the next one after that is the 5th harmonic?
You got it. And then the 7th harmonic. So just make sure that you are understanding that. When you look at the actual frequencies of those higher level harmonics, the second harmonic that you see, the second frequency that you see that's a harmonic is going to have a frequency that's 3 times the fundamental frequency. That integer multiplicity is the harmonic number. So just again, be aware of that, point that out, because it's something that often gets overlooked. And I'm sure will happen again, but not with you guys, not with you guys here, because you're here knowing what's going on. So again, screenshot, all that great stuff. And then you are going to look at your ah sound. So you are going to produce an ah sound and open it up in Raven. The easiest way to do this is by using Audacity. I'll just go ahead and say that you can record into Raven, but depending on whether you have the full version or just the demo version, there's all sorts of things that you have to do. It's much, much easier if we just go into Audacity. Oops. Get that down, go into Audacity, dun, 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 and open it up. Bum, bum, bum. I gotta search for it. AUD. And record your voice directly into Audacity, then save the sound file on your computer, and then open it up with Raven. So let me demonstrate. So we've got Audacity here. Great. I can lay down a track, just add a new track, just a mono track. That's good. And then we can go ahead and there's this record button. Somewhere on your Audacity screen, you should have the ability to press record. You may have to go into tools, no tracks, transport, view, select, edit. On other systems, tracks. There should just be a record button somewhere. And record. So when you say your ah sound, you need to say it nice and monotone. Don't go ah. That's not monotone. We want one nice clean ah sound, and it's ah. It's not a, the vowel a. Don't say a. It's ah. Try to sustain it, nice and clear, enunciated, and go from there. Make it 1-2 seconds long. It's fine. Ready? Ah. Go ahead, stop the recording. Bam. I've got this nice little section right here that would be my ah sound. And I can just go over to File and go to Export and then export as a WAV file. MP3 is okay too. I would stick with WAV files. They have more integrity, larger sound files, but export as a WAV file. Great. And then it's going to say, where do you want to put it? You want to put it somewhere you can find it. So the easiest place to find things, in my opinion, is on the desktop or in some folder that is for this course in specific. I'm just going to throw it on my desktop and call it, what is, today is 11/2. So 11/2, I'm going to go ahead and save it. It says a WAV file, great, 16 bits, that's fine. Save it up. This stuff, I'm not worried about artist name, all that stuff. I just say, okay. And now, if I go over to my desktop, oh my gosh, look at that. I got this sound file right there. Well, what I want to do is be able to open that up into Raven. So let's do that. How are we going to do it? Hey, we have Raven open. We go ahead and go to File, go to New. Nope, we don't go to New. We can just go Open Sound File. Fantastic. And then we can go over to our desktop itself, because that's where the file is. And there it is right there. Look at that. 11/2. So I'll go ahead, select that, and press open. Want to change it to physics of music default setting, press OK. And voila. There it is. There it is. And I can make sure by taking that little section and playing it. So let me do the screen share sound, share. So I just highlight this little section. I'm going to play it, make sure that's my ah sound. Wow. Fantastic. There's my ah sound. Well, what we want to be able to do is zoom into the ah sound and be able to see some things. So first off, I'm going to take my spectrum slice locator line so I can see what the spectrum looks like. And I want to find a portion here where it's a nice clean spectrum. Notice that my spectrum changes. I got some wobbliness in my voice, maybe a little natural vibrato, definitely not a clean, musically honed vocalist by any means, but you could definitely see you got some really, really clear harmonics here, right? Then at this particular location, things get really jumbly over here. So maybe I want to take it for somewhere that's a little cleaner, like, oh, that's pretty clean right there. That looks like about as clean as it's going to get. And then we could zoom in right around that time. So go ahead and take that, zoom in there, and then I could continue to zoom in to kind of see what my waveform looked like. There's my waveform. That's what my voice looked like when I was saying the ah sound around 1.528 seconds into the recording. Great. Also, want to be able to appreciate this spectrogram slice right here. Look at this. This is looking specifically at the individual frequencies that are in my voice's sound at that moment in time. And what's something that you can notice about both of these graphs here? One, hey, the waveform graph, is that periodic? And the answer is, within reason, definitely. Doing the same thing over and over, maybe some minor alterations from cycle to cycle, but the overall length of a cycle looks like it's going to be the same. I could go from there to there and get that. I'll answer the question one moment and get that the period is about 0.006349. I can come over to this one and say from there to there's also one cycle, 006457. Those are within reason, going to give within a hertz or so the same frequency. So that's one thing to notice. Got a nice periodic tone here. Vowel sounds are harmonic tones. And then we've got these harmonics here. If I start looking at these, it looks like they're all evenly spaced, right? The distance between this one and this one is the same as this one and this one, is this one and this one, is this one and this one. That's indicative, again, of something that is a harmonic tone. We have equal spacing between the individual frequencies. So all these higher order frequencies here are all integer multiples of this one right here, which if I cared to go ahead and say, hey, what is the approximate frequency that I said that at? That was right around 160 hertz, give or take a little bit. But that's what you want to be able to do. If I want to look at what was the greatest contribution within my voice frequency-wise, it looks like it was the fourth harmonic. I want to be sure I could always extend that out a little bit and see, oh yeah, the fourth harmonic, that one's definitely the most intense, followed by the third harmonic, followed by the sixth harmonic, then followed by the first harmonic. I could basically make a little table that says most intense to least intense over the first 10 harmonics or so, or 10 most intense harmonics. And yeah, it's going to just depends on your particular voice, emphasis in the sound. Everybody has something different, but there are certain patterns that will be the same, and we'll get into that later. It's got a couple of, oh, you're shocked, you're shook. Ooh, I like that. Oh, a beautiful voice. Oh my gosh. Man, you're messing with me. Anyways. I thought you were shocked at the spectrogram slice. Oh shoot, you cracked me up. Anyways, we've got ourselves, the ability to look at our voice. I think that's pretty cool. Go in and measure your own fundamental frequency. I could go back and look at what the closest musical note is to what I just said the ah sound at. You can look at variations, look at where energy is concentrated, and that's what we want to be able to do overall in analyzing sounds. Understand the composition of it. Where's energy concentrated? What produces, not produces, but why does the sound the way it does? And it's all in here. It's all in here. These are all the frequencies that join together to produce the uniqueness that is, for better or worse, my ah sound. Fantastic. All right. So let's just come back to that Zoom. He's not coming back. There. Come on, Zoom. Screen sharing. Why is it messing with me? That's because I did this. Screen share. Stop share. Whew, scared me for a second. All right, so that's really it. Playing around with some sounds. Make sure you're opening up the right sound files. The bottle resonance, open, closed, and then recording your own sound. Other ways to do it, you can record directly into Raven, or record on a phone if you got a voice recorder, and then email it to yourself, then save it on your computer, then open it. But again, using Audacity is easiest, in my opinion. Questions? Very well then. You guys have a wonderful rest of the day, rest of the week. Nice weekend. Stay safe, be well, and see you next time.
Thank you, Professor.
Thank you, Stephanie.